Hello, and welcome to Mastering Probability and Statistics in Python. If I say data science stands on the shoulders of probability and statistics, I might not be exaggerating. That's true. All the recent advancements in data science and machine learning, they can be traced back to the fundamental concepts of probability and statistics. Even some statisticians say that the data science and all its recent advancements, they can be just modeled as a branch of statistics. The importance of the subject can be realized by the fact that, for example, consider an example of a deep neural network that is being trained for months and months on petabytes of data, very large amount of data. But after all that training, at the end of the day, the result of the training is a probability model. So all that effort of months on petabytes of data actually come up with a probability law. I mean, you learn a probability law. So yeah, I mean, this is extremely important subject, particularly for data science and advancements in data science. So let's dive in. Let's dive in by focusing on the very basics and very fundamentals of the subject. So we start with the question, what is probability? Well, probability as a theory deals with predicting the confidence or likelihood for future events, something that is going to happen, how likely it is that it is going to happen. And probability as a number is basically that number is modeled between 0 and 1. 0 and 1. 0 means something that we are curious about. If the probability is regarded as 0, that means it is not going to happen for sure. And if the probability is regarded as 1, then that means the event that we are curious about will happen for sure. And any number in between, for example, 0.73 means we are 73% confident that the event will happen. So probability as a theory, it deals with the rules and laws of rules and laws and all these kind of mathematical derivations that deals with predicting the confidence or likelihood for future events. But probability as a number is that confidence value for the future events. Statistics, on the other hand, involves the analysis of frequency of the past events. So it is good to notice the difference between probability and statistics, although they work in common, and most of the time the terms are used interchangeably. But it is good to notice the difference between the two. If I say that in probability theory, we need laws that help us predicting the future. So we need certain laws or rules that are required to draw predictions in the future. Then statistics, the goal of statistics is to come up with those rules from the data. So statistics actually draw rules from the data that is available, historical data, the data that is available to date. It analyzes the data, maybe visualizations of the data, all different sorts of analysis on the data, and somehow come up with the rules that governs the pattern and the laws. And once the rules and laws are available, the task of probability or the probability theory or the probabilist, the task of that is to get those rules and make the predictions about different kind of events in the future. So you can think about the difference between probability and statistics in the following timeline way. So think about that's the time that's the time that is going on, And here at this particular stage we are sitting. So let's say we are sitting right here. And this is all the data that is available. And these are all the events that happen in the past. And right now we are here. And we want to predict what happened next. For example, we want to predict the likelihood or the confidence of something that can happen at this particular time interval right now here. And right now we are sitting here and we want to predict what is going to happen here. Now, sitting here, the task of a statistician is to look back to the data and come up with the rules and laws and patterns that can help for making predictions in future. Once you go back and see all the data, you analyze a lot of data, you apply all kind of artistic skills and scientific skills, whatever you want to, but you come up with the rules. Once the rules are available by looking backward to the data, now the task of probability or probabilist is to look forward and use these rules and make predictions. Obviously, if we have more data, if we can come more data, if we reach, for example, at this point in the timeline, we might have more data, and a statistician may go back and refine the rules if the rules are refinable. But the distinction here can be made in a way that you look back to the data and come up with the laws and rules and patterns. And then using those laws, rules, or patterns, you look forward in the future and make predictions. So looking backward is what the statistics is about. Looking forward in future is what the probability is about. So it is good to notice this distinction. But in practice, the terms probability and statistics normally used interchangeably, or sometimes people just use the term statistics, although it is good to notice the difference between probability and statistics. People even say probability is pure mathematics and statistics is like an art. I mean, there are a lot of phrases out there. So yeah. Next we see what sets are. You might be thinking, well, why directly from probability to sets? Well, I would say probability theory, it uses the set theory extensively. I mean, it uses the set extensively to build all these kind of data structures and structures to make predictions and stuff like so. So it is good to just get comfortable with what a set is. Set, in a very layman terms, is a collection. It is a collection. First of all, it's a collection. Like you have so many collections at home maybe, or in your office or something like so. A bookshelf, for example, is a collection of books. Your bag that contains maybe your laptop, maybe the charger or the batteries of the laptop, or maybe some books or notes or stuff like so, that is also a collection. So set at the end of the day is a collection. But not every collection satisfies to be qualified to be called as a set. A collection that has two properties, property one is the collection must be unordered. Let me write that. The collection must be unordered, which means in the collection there should not be positioning of different objects. So you have collection, you have different objects. Which object is at which position in your collection? If that is not a matter, then we will say the collection is really unordered. There is no positioning of different objects inside the collection, or shuffling the objects here and there does not change the collection. If that's the case, then we will say the collection is unordered. The elements of the collection, they have not designated positions inside the collection. So one property of the collection is unordered. The other property is They must all be unique or distinct. There shouldn't be any copy of the object. So if I define the set, it's a collection, let me write unordered collection of distinct objects. Here we need to focus on some words: collection, unordered, distinct, and objects. Objects can be any objects. I mean, they can be books, they can be, any objects in the collection. So as long as you have a collection and it is unordered, all the objects, they are unique, there is no object having copy in the collection, we call that collection as a set. Normally in mathematics, the set are written in these curly braces that represent a collection. For example, this is a collection and this is a set, and it is always good to denote set with, rename the set with some nickname, so that whenever you want to refer the sets again and again, you can refer the sets with their names. And about the objects inside the set, they can be any objects. I mean, they can be numbers, strings, tuples, they can be other sets inside the sets. All these things, I mean, this 1, 2, 3, they're called members of the set. And for example, 1 belongs to this set. However, 5 does not belong to the set. So a set can have any kind of members, any mixture type of members, no matter what. However, a common practice is to keep the sets of same kind of objects where the similarity is defined in certain way. Keep those kind of objects in different kind of sets. For example, set of numbers, set of strings, set of locations. These might be different sets, or maybe you dump all the numbers, all the locations, and all the strings or names inside one set. That is allowed, as long as it's an object that have some definition. You can just include that object inside the set as a member. And again, the set can has other sets as members, because there is no restriction on the object that is there inside the collection. So this should be noted. Next, we talk about some operations on the sets. What kind of operations that we can perform on the set? There are a lot of operations. Let me list a few of those. For example, union of two sets. Union operation, let's say we have set A, 1, 2, 3, 4. And let's say we have set B, which is, let's say 3, 5, 4, maybe 1. Let's say we have these two sets and we take their union. So the union is normally written as A union B with this U symbol. And the union is just the union of the two sets. That's just you combine the two sets together, but because the definition of the set does not allow the duplicates, you just represent all the values that occur in both of the sets just once in the resultant set. So for example, 1, 2, 3. 3 does not occur twice, although when you combine set A and B, 3 should appear twice. But in the resultant set, because the result is also a set, and set cannot contain duplicates, so this 3 will not appear twice. Similarly, this 4 will not appear twice, and this 1 will not appear twice, and then this 5. Now you can see in A union B, this is a set. Both B and A, they are subsets of this set. A subset is just a set that contains all the elements of the parent sets. So we can say A is a subset of A union B, which means all the elements of A, they are also there in A union B. Similarly, B is also a subset of A union B, which means all the elements of B, they are also there in A union B. So that's what a subset is. Because we talked about subset now, it is good to talk about an empty set. If we have, for example, a set 1, 2, 3, 4, then this particular set, for example 2, 4, that's a subset of A because all the elements of this set, they are also present in A. And there is no element of this set that is not present in A, so this is called the subset. About the subsets, empty set is also a subset of every set. That's by definition. People define empty set to be a subset of every set. And further, the set itself is subset of, every set is subset of itself. That is also a definition. These two things are a little more, these two things are, these may be confusing, but it is good to note that empty set is defined to be a subset of every set, and a set is subset of itself. Even sometimes equality between two sets is established, like if A is a subset of B and B is also a subset of A, if these two things happen at once, that means A and B, they are equal. So sometimes the equality in set that is also defined like using the subset operations. Yeah, so there are a couple of more operations. Let me move on to the operations one by one. There is another operation called intersection. Intersection. If you have set A, let's say 1, 2, 3, and 4, and you have set B, let's say 2, 4, 9, then the intersection of two sets written in this form is just the common elements between two sets. What are the elements that are common to both of the sets? In this case, 2 and 4. This is common to both A and B. It is also important to note that A intersection B is always a subset of A, and A intersection B is always a subset of B. Even if the intersection is empty, even if A and B, they both have no element at all that is common, then the intersection will be an empty set. And because empty set is a subset of every set, so these kind of rules, they hold for empty set as well. One more thing about empty set, sometimes this empty set is also denoted by this kind of symbol. But it is worth to mention that if a set contains this empty set as an element, this set is no longer empty because it has an element, and that element has a particular definition. The definition of this element is it is an empty set. So that's an object inside this set. So this set is no longer empty, although this set is an empty set, and this is also an empty set. So these kind of distinctions should be noticed. Other than intersection and union, we have difference, A minus B. Normally this A minus B is written as, the set difference is written as with this kind of this kind of slash, but it is okay to write minus as well, although this minus is more common notation. This slash is more common notation in sets. So whether you write A minus B or A slash B, that means the set difference. The difference between two sets, A and B, so A minus B is the elements of A that are not present in B. So for example, take an example of set A and set B here, and we say A minus B is all the elements of A. So A minus B is just a set of elements of A, but those elements that are not in B. So for example, the element 1 is not in B, so we list that in A minus B. Element 2 is in B, so we will avoid this element. Element 3 is not in B, so we will write that. Element 4 is also in B, so we will not write that element. So A minus B is all the elements of A that are not in B. Similarly, B minus A is all the elements of B that are not in A. In this particular example, B minus A would be 9 because the elements of B that are not in A, that is simply 9. Another thing that appears from this set difference is sometimes we denote one particular kind of set as universal set. sometimes denoted as omega. Universal set is a set that is assumed to be a set that all the sets that are of our interest, they are subsets of universal set. Each and every element that is the element of interest that belongs to universal set. And all the sets that we are talking about, they are subsets of universal sets. So you can think the universal set as containing the whole universe, and everything in between the universe are substructures that we might be talking about. If universal set, for example, here, let me define the universal set to be, just in case we are talking about just the elements, just the numbers from 1 to 10, let's say that's whole our universe. We talk about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say that's our universe. All the sets, they are subsets of this, and that's our domain we are working in. Then a complement can be defined as simply as a set difference, all the elements of the universe that are not in A. So that's a complement. Similarly, we can define complement of any set that is the difference from universal set to that particular set. So that's the complement. Further, we can define, just in a connection of intersection, we can define disjoint sets. Disjoint sets, the two sets are called disjoint if their intersection is empty. If there's nothing in common, then the sets are called disjoint. And the definition of this disjoint sets can be extended to multiple sets as well. Another related concept is partition. A partition is basically, so let's say we have a set S, and we have some of its subsets, let's say S1, S2, and S3. Let's say we have a set S, and we have other sets S1, S2, and S3. We want to see whether S1, S2, S3, they form a partition of S or not. Well, forming a partition of S means all the sets S1, S2, and S3, first of all, they must all be subset of this S, and second, their union must be the parent set S, and third, there should be nothing in common. So S1 intersection S2 is empty, S1 intersection S3 is empty, and S2 intersection S3 is also empty. So if you have subsets that are all disjoint and their union is the parent set, and in that case we will say these sets, they form a partition of this particular set. Now, coming back to complements, there are certain beautiful kind of laws by De Morgan that I should mention here, that if you have A union B, if you have two sets and you take their union and then you take complement of the union, that is equivalent to A complement intersection B complement. That's one De Morgan law. The other De Morgan law just flips this union and intersection from left hand side to right hand side, and that works. So so these are kind of very basic kind of operations in the set. We will be seeing the operations and the definition of the sets in Python as well. So let's go to Python and just get comfortable with the definition of set, what the sets are, what the subsets are, and let's get comfortable with the operations on the set in Python. Yeah. Let's go to Python and just define some set. Let's say A is a set. Let's say 1, 2, 3, maybe 8. Let's say this is set A. Let's define set B. For example, maybe 3, 4, maybe this. And what you can do next is you can, for example, check a membership relationship. For example, if you want to set 1 in A, print that out. If you want to print that, if you want to check whether a particular element is in A or not. So here we want to print, the print will become true if 1 is in A, otherwise it will become false. So in this particular case, yes, 1 is an element of A. However, if you just write, for example, 4 in A, you will get false. Yeah. So basically this 4 in A, that is basically a variable. You can call it a flag. The value of this, that's a Boolean variable. The type of this variable is Boolean. It has only two values, true or false. So you can check the membership of this with that. Further, you can check whether one set is subset of the other or not. So for example, you can, for example, define a set. Let's say you have a set B already. You may want to check whether B is subset of A or not. So there is a function that is available. So B is subset of A. It will return true. The value will be true if B is the subset. Otherwise, the value will be false. So here false because B is not a subset of A. B contains a value 4 which is no longer in A. So this 4 does not belong to A. So B does not have all the elements that are drawn from A. B has some elements that are not in A. Hence, B is not subset of A. Just for fun, why don't we write our own function? Now this is subset function is available. Why don't we write this function by ourselves? So let's write a function. The function name might be check. So let me f is subset. Let's write this function as this way. And not only that, we pass the two sets here, A and B, and we want to check whether A is subset of B or not. So let's say that's the function that we really want to write. So basically we want to write to check whether the first set is subset of the second set or not. So yeah, this is something that we really want to write on our own. So what can we do in this function? For example, we can because we want to check whether all the elements of A, they are present in B, we will loop over the element of A. So for element E in A, check if E in A in B pass, else return false. That's it. So for example, it will go over every element of A and will check whether that element is in B or not. If that element is in B, it will continue. And if there is a single element that is not in B, if there is a single element of A that is not in B, which means you will go in return, you will go in this statement and you will get a return, and then you will return false. If the loop completes, for example, then you just write true, because in that case, everything is okay. So that is our own function, finding subset. By the way, if you're not comfortable with Python, we have a full-fledged course on Python for beginners from scratch. We have actually introduced Python at a very beginner level to a little bit advanced level in our separate course. So I will suggest, if you're not comfortable with Python, you should enroll that course as well, because in this particular course we will use Python heavily. So yeah, so let's do that. And now let's see whether a particular so let's print f is subset. So let's say we want to check whether B is subset of A or not. So the return is false. B is not a subset of A. If, for example, we print just f is subset, our own function, and we check whether this particular 2, 3, 4, whether this is a subset of this particular set or not, which contains 1, 2, 3, 4, 5, and 6. Now the return value should be true. Let's check. That's true. Yeah, that's true. Yeah, that's true. Actually, actually, this is subset function that you have seen earlier. That is also available built-in function. But that's how you can implement the function if you really want yourself. Okay, here is a Python question for you, um, which might be a fun practice. Write a function that takes a set and prints all its subsets. So basically, or write a function that actually takes a set and returns a power set, and then you just print the power set. Yeah, do it. It will be a fun exercise. Okay, next we do some practice in Python of the operations that we did for sets, for example, union, intersection, difference, complements, and all that stuff. So let's go to Jupyter Notebook and do some practice. What are the functions that are available for these set kind of data structures? So for that, maybe we need a NumPy package. So let's import that as np, and let's have a universal set. Let me call that set as omega, or universal set, maybe let's call that omega, omg, omega. Let me call the set command on that, and np dot arrange. This arrange function actually returns, for example, this arrange function returns the numbers from 0 to 9, including 9, not 10. And then this set command will generate that NumPy array as a set. So for example, if we now see type of OMG, that will be a set rather than a NumPy array. So we can just display that. That's a set of these 9 numbers. Let's say that's our universe. Let's say that's a universal set. Let's define a set A to be let's say set, let's say np dot range, start from, let's say 0, end at 9, and pick every other element. Let's say that's our A. If you see A, let's say this is A, and maybe let's define B, for example, as a set np dot arrange, just to take an example, np dot arrange, start from 1, go to 9, and pick, for example, every third element. So this B is this is B, this is A. Now if you see the union of A and B, I will call union function A union B, and the result will be this. You can see A contains 0, 2, 4, 6, 8, and B contains 1, 4, 7, and here we have A union B, which is both the elements of A as well as the elements of B, but this duplicate element, this 4, is appearing on both of the sets, and that is just represented once. Further, we can take the intersection A dot intersection B, and this will result just the common elements of A and B. And here the common elements of A and B are just 4. If there are more than one common elements, for example, if we just add with B dot add, let's say another element, let's say we add 6 to B as well. Now if you see B has these elements 1, 4, 6, and 7. A has elements 0, 2, 4, 6. If we now take the intersection, we will be noticing 4 and 6 both. So let's see A dot intersection B. Yeah, so that is 4 and 6. Other than intersection, there is a difference function as well. Again, let me display A, that is A. Let me display B, that is B. A dot difference will give me the difference of A and B. So A minus B, the result will be A minus B. All the elements of A that are not in B, so 0 is not in B, 2 is not in B, 8 is not in B. The rest of the elements of A, they are in B, so they are discarded. Similarly, once you have defined this universal function, universal set OMG, you can compute the complement of A. So A complement, for example, A complement is simply universal set dot difference A. That is A complement. And here you can see A complement as all the elements that are there in the universal set, but they are not in A. Similarly, you can define B complement the same way. I'm just going to prove the De Morgan's law for you. B complement is just that is B, and this is B complement. So this is B complement. So here is the De Morgan's law, for example. De Morgan's law say that A dot union B, and then you take the complement of that. I mean, this thing. This is A union B, that's a set. Then you take the complement of that, which is OMG dot difference. So yeah, that's a difference. So first you take A union B, and then you take the difference of A union B from the universal set, that is A union B whole complement. And this result will be the same as if you take the intersection of A complement and B complement. Let's see, A complement dot intersection B complement. Yeah, so the result is exactly the same, and that is one De Morgan law. The other De Morgan law is the other way around. You write an intersection here and you write a union here, and you're done. So let me prove the other way around as well. So if you just write the intersection here, intersection, that's one side, or you can call it the left hand side. The right hand side might be this, with this intersection removed with union. And you can see both are exactly correct. I mean, this is not a complete mathematical proof. I'm just showing you what De Morgan's law says. Yeah. So further, you can also check whether the two sets are just disjoint or not. There is a is disjoint function. There is a is subset function you have already seen. There is a function called is superset. I mean, whether a particular set is a superset of other set or not. There are a lot of functions and support available in this sets data structure in Python. So it is good to explore that. Okay, next we talk about some of the terminology related to probability models, and we start with experiment. Rather than defining experiment, let me define random experiment, because that is I mean, writing this prefix random makes much more sense when we talk about experiments. Experiment is any procedure that you do that have more than one outcomes, maybe several outcomes. So for example, you might end up flipping a coin, and the outcome or the result of the experiment, so you flip a coin, the outcome, that's an experiment. You flip a coin. Now the outcome of that experiment might be a head, or it might be a tail. So that's what the experiment is just flipping a coin, and the outcome might be head, might be tail. We do not know whether it will be head or a tail, but it can be one of the several outcomes. So that's an experiment. On the other hand, if you roll a die, for example, that's an experiment. You roll a die, that's an experiment. And the outcomes now are, maybe it comes up 1, it maybe comes up 2, 3, 4, 5, and 6, where we are assuming that the die has 6 faces. You may have another complicated kind of experiment in which you have a coin in your hand. In one hand you have a coin, and in the other hand you have a 6-faced die, and you simultaneously toss a coin as well as roll a die. That's experiment. And now the outcomes might be the coin may end up as head, and and the die may come up with one. That might be one outcome. Another outcome might be head with 2. Another outcome might be a head with 3, so on, a head with 6. That are, I mean, each of these is one outcome of the experiment, or all these with the tails. In this particular case, we have 12 outcomes, possible outcomes for this experiment, and one of these outcomes is going to happen as a result of the experiment. We call the experiment random because we do not know which outcome will appear. It is completely random. Even though if the coin is biased and it has, it is constructed in a way that the appearance of head is more likely than the tail, even if there are chances of the tail to appear, even if a very small chances of a tail or head is there, we will still call the experiment at random, because even though there are high chances of head due to the construction of the coin, the randomness of appearing as a head or tail is still there. So the experiment is called random because whatever outcome the experiment will result, that outcome is random. We do not know what that outcome will be. And obviously the goal of probability theory is to predict those kind of outcomes. What are the chances that this outcome will appear? What are the chances that this outcome will appear, and so on? That we will see later in this video. But it should be clear that an experiment, normally random experiment, is some procedure that you do that may have several possible outcomes, and which outcome is going to appear as a result of this experiment is random. Which means if you repeat the experiment, maybe another outcome appear. If you repeat the experiment again, maybe another outcome appear, and so on. So that's why you do not know which outcome can appear, and so the experiment is called random. Third, we talk about sample space. Basically, the set of all outcomes of an experiment. If you just write the set of all the outcomes of an experiment, that is called a sample space. So sample space is simply you list all the outcomes in a set, and that is called a sample space. So this is, for example, sample space of experiment 1. This is sample space of experiment 2, and this is sample space of experiment 3. So set of all possible outcomes where no single outcome is left out, and there is no element in this set that is not going to occur. I mean, all the possible outcomes then that can appear, all possibilities, you just list them in a set, and that is called a sample space. Third, we talk about event. Fourth, we talk about event. Event is any subset of sample space. When we talk about subset, we may end up confusing the event with an empty subset, because empty subset is also a subset. Events normally are non-empty subsets. So you have a sample space, and an event might be any subset of that. Consider, for example, you roll a die. That's your random experiment. The sample space for that, let me denote the sample space as S, or in our case, that is basically the universe. So let's denote that as omega. That's all the possible outcomes for a 6-face die. Yeah. So you roll a die. That's the and one event might be, you might be interested in, or you might win the game if an even number occurs, any even number. So this might be an event. If 2 occurs, if the outcome 2 appears, then you may win the game. If 4 appears, you may win the game. If 6 appears, you may win the game. So basically, for winning, you are interested in this particular event to occur. We say an event occurs if any of its outcome appears. So if you actually roll a die and a 2 appears, then we say E occurs, the event occurs. The event occurs even if a 4 appears. And if you repeat the experiment, for example, and a 6 appears, we say event occurs. So occurrence of event means any of its outcome basically appears as a result of random experiment. Now we move towards probability model from event to basically a number. Consider, for example, consider again, your coin is fair. That's your assumption. Your coin is fair. And the experiment is you toss a coin. So the sample space basically is heads and tails. That's the sample space. Now what's the probability? Maybe you're interested in an event. You are interested in an event that a head appears. That's one event. Let me call that event as E1. Maybe another event is a tail appears. In this case, we have these two kind of events. Let's say events of interest. Now the probability of event 1 is just a number, that actually signifies the confidence of E1 to occur. If the coin is fair, for example, if there are 50-50 chances of heads and tails, then the chances or the predictions that a head will appear or this event will occur, that is 0.5. Because later we will see the probability numbers, they range from 0 to 1. 0 means no chances, 1 means 100% chances or certain, and inside it is the relative scale of probability. Similarly, the probability of E2 is 0.5 in this case. But it might be possible that the coin is constructed in a way that the probability of head or event 1 might be 70%. The construction company of that coin just reveals that the coin is biased and the head is 70% as likely as the tail. In that case, the probabilities will be that. And but what these probabilities will be, you have to rely on that. Or if you have a toss, if you have a coin, then toss that coin several times and see, for example, toss that coin 1,000,000 times and see what fraction comes up as a head and what fraction comes up as a tail, and that will give you a reasonable estimate of the likelihoods of what is going to happen next in future. But finding out these probabilities from data, if you toss that coin several times and you come up with these kind of rules of probabilities, that's a task of statistics. But once the rules are available, then you are doing prediction on the upcoming events. That's a task of probability, as I mentioned earlier. Further, we can have, for example, let's say we have roll a die and 1, 2, 3, 4, 5, 6. And let's say we have an event of even numbers. So 2 appears, 4 appears, 6 appears. So we are interested in, for example, what's the probability that an even number appears? Well, that's a probability that the 2 appears, or so probability that event occurs with 2, that probability. So let me write that as 2. Then the probability that a 4 occurs, then the probability that a 6 occurs. So you add up all these probabilities and that's the probability of event. So if event has more and more outcomes, it is more likely to occur because one of its outcome becomes more probable to appear as an outcome of the experiment. Next, we talk about some axioms of probability. Actually, first axiom and the foremost axiom is the probability of any event must be non-negative. That's the first, or that's one axiom. That's one rule. The probability you assign to any event must be non-negative. Another axiom is, or the other rule is, the probability of two events, E1 union E2, if you have two events. Remember, this E1 is a set, E2 is a set, E1 union E2 is eventually a set. That is basically probability of E1 plus probability of E2 if E1 and E2, they are disjoint. If they are disjoint, then the probability of E1 and E2, union E2, is simply the probability of the addition of probability of both events. If they're not disjoint, I mean, the more general formula of this is like this. They may be disjoint, or they may not be disjoint. In that case, you have probability of E1 plus probability of E2 minus probability of the intersection, because the intersection is counted twice. Remember, the intersection elements, they appear in E1 as well as in E2. So towards the chances computation, they are counted twice. So we have to subtract one of its contributions to balance out the overcounting that we did. And in that case, the probability of an empty event, or the event that is zero, with this assumption that the probability of phi, or empty event, is zero, this formula is consistent with the formula of disjoint events. And this is also true for more than two events. If you have several events, if all events are mutually exclusive or disjoint, then the probability of the union is just the sum of all the probabilities. The third rule is the normalization rule. The probability of the sample space itself is an event, but that event is certain. Remember, the sample space, one of the outcome of the sample space is going to happen. So what's the probability that sample space occurs? Sample space is also a set, that's an event. If that set is treated as an event, that is for sure to occur, because one of the outcomes of the experiment is going to appear, and every outcome is in the sample space. So this is for sure true. So I mean, first of all, the probability assigning to every event is non-negative. For mutually exclusive events, the probability of union is just the sum of individual probabilities. And even if they are not mutually exclusive, even if they are not disjoint, you just account for the overcounting you did, and the probability of sample space, which is the sure event, that is 1. So that way the probability of any event stays between 0 and 1. So yeah, I mean, these axioms should be kind of rules must be taken care of. There are several rules that you can now, for example, derive. For example, if A is a subset of B, then probability of A is smaller or equal to probability of B. That is the direct consequences of these rules. And there are several other rules. For example, let me write probability of A union B is always smaller than or equal to probability of A, probability of B, where A and B are events. And this becomes equality if A and B, they are disjoint. Otherwise, this will stay smaller and this will stay larger. Yeah, so, and there are several conclusions that you can make on different kind of relationships among different kind of events. Remember, each event is a set. Next, we talk about conditional probability. For example, what do we mean by conditional probability? Well, if you, for example, let me explain the conditional probability with an example. Let's say you roll a die, for example, and your sample space is this: 1, 2, 3, 4, 5, 6. Let's say that's your sample space. Assume event EI is simply I, where I varies from 1 to 6. So that's event I. And further assume all the events, all the outcomes, they are equally likely, which means this is 1 over 6. So the chances that 1 appear is 1 over 6, the chances that 2 appears is 1 over 6, the chances that 3 appears is 1 over 6, and so on. So so now let's say you have an event. Let's say you have an event E event. Let's say this event, which is 2, 4, and 6, all the even elements. Let's say this is event E. Now, the probability that E2 occurs, E2, remember here E2 simply means that the outcome is 2. That probability is 1 over 6. But imagine if you just if you are going to do the experiment, if you're going to roll a die, and before rolling a die, somehow you have a belief that this event will occur. That is somehow belief. Your belief is that this event must occur. Somehow you have this information that this particular event will occur for sure, or this event is certain, for example. In that case, how will you utilize that information in estimating this probability? Well, without that information, the probability of the event E2 is 1 over 6. But with this information available, the probability of E2, given the information that this particular event must occur, now the probability of E2 changes in a way that because this event is going to occur for sure, your sample space changes. And now your sample space becomes this. Because if this is a certain event, this is going to happen, then all the outcomes in this particular event, one of them, they are going to appear for sure. So now this becomes your sample space. And in this particular sample space, what is the probability that a 2 will appear? Well, all the probabilities, they are equally likely for normalization if you normalize that. So the probability of this 2 occurring is 1 over 3. The probability of this 4 occurring is 1 over 3. The probability of this 6 occurring is 1 over 3. So in that case, the probability will become 1 over 3 rather than 1 over 6 because you have utilized this particular information. So conditional probability is probability of an event conditioned on the information of some other event. So for example, if some event is going to happen for sure, and you have that information, then the probability of events, they may change after utilizing that information inside the model, and all that stuff is known as conditional probability. And by the way, conditional probability is just another probability law after you have utilized your condition inside. So using the condition will change the sample space. Once the sample space changes, all the probability of different events, they are renormalized so that they add up to 1, and the probabilities, they will get changed. So the formula, for example, is the probability of A given that B must occur. What is the chances that A will occur? Given that we know that B must occur or B will occur for sure, that is the probability that both A and B will occur. The chances that A and B will occur, both of them, divided by the probability of B. So you now can think that this probability of B, this normalization factor, that is like the sample space normalization. B is acting as a sample space, and A intersection B is acting as an event from this particular sample space. We are not getting anything that is outside B. So that's what the conditional probability, in a very crude sense, in terms of events, what conditional probability is. Next, we talk about the total probability theorem. That is very, very powerful theorem that uses this conditional probability. So for example, what's the probability of, let's say, A? A is some event. The probability of A is the probability of A and B1 plus probability of A and B2 plus probability of A and B3. I will shortly tell you what do we mean by B1, B2, and B3 and all that stuff. Assume B1, B2, and B3, they are disjoint events and they form a partition of sample space. So assume B1, B2, B3, they are a partition, they form a partition of sample space. Then probability of A, how can you calculate the probability of A? The probability of A then is probability of A intersection B1. So what's the probability of A? The probability of A is the probability of what's the probability that A will appear? Well, A can appear as along with B1, or A can appear along with B2, or A can appear along with B3. That's it. That's a probability. And that is known as the total probability theorem. In the last slide, as I have mentioned, you can have seen this formula. Let me rewrite that formula again. And here, this probability of A intersection B can be written as probability of A given B into probability of B, just by the formula that we saw in the last slide. If we just pull this B over here, we get A intersection B to that. And with that, this particular total probability theorem becomes probability of A given B1 into B probability of B1 plus probability of A given B2 into probability of B2 and probability of A given B3 into probability of B3. And these partition sets need not to be just only 3. They can be 2, they can be 3, 4, 5, 7, or maybe countably infinite. They may be infinite of those, but they should be countable. So yeah, so that's the total probability theorem, and very, very useful in a lot of cases. One very powerful use of this conditional probability is also there in Bayes' rule. So Bayes' rule is the following. So consider, for example, you know that in sets A union B is the same as A intersection B is the same as B intersection A. That's no doubt. That means so A intersection B and B intersection A, that's the same set. So now the probability of A intersection B must be equal to the probability of B intersection A. But by conditional probability law, we know that probability of A intersection B is probability of A given B into probability of B, which is equal to probability of B given A into probability of A. And here we can just see probability of B is probability of A given B is from the left to right. It is probability of B given A into probability of A and divided by probability of B. That is called the Bayes' rule, and it is used extensively and heavily in inference. Almost all the classifiers, all the machine learning stands on this rule. And that rule comes very naturally through the conditional probability. So probability of A given B is simply probability of B given A into probability of B and divided by into probability of A divided by probability of B. I will show you the examples of Bayes classifier and inference. Actually, we will implement that in Python in the next video series as well. I mean, this is the first part of the video series. In the next part of the video series, we are going to implement all these concepts that we are seeing here in Python as well. But it should be noticed that this simple rule, I mean, very natural and simple rule that can be derived very easily with a few steps, all the machine learning, all the classification, all the regression theory stands on this. All the estimation, that estimation is whether the maximum likelihood estimate, the parametric estimation, or the maximum a posteriori distribution map estimators, even Bayesian estimators, they all stand on shoulders of this Bayes rule. And there are direct ways of estimating this left-hand side without actually countering the ingredients, and that is called, sometimes called in machine learning, that is called discriminative learning. And if you learn this left-hand side using the individual components, for example, this component and that component and that component, you learn all these three first and then you arrange them in this way and you actually got the formula for this. That is called the generative learning. Both have their benefits, merits and demerits in machine learning, but any machine learning model is either generative or discriminative. One way or the other, you are calculating this left hand side. Let me give you an idea. For example, what's the probability that a face image that appears right now, the face image that appears right now has identity, let's say 5. It's a image of the fifth person where the image is just appears right now, that image. What is this probability? By Bayes' theorem, we can see that the probability of this is into probability of y equals 5 and divided by probability of x is image. Although I'm talking here in numbers, in variables, not as events, we will see later on we can convert the events to variables called random variables. But just to show you that all the, classification and regression theory, they use these kind of formulae to build face recognition systems, to build object recognition systems, to build speech recognition systems and all that stuff. Each and everything is there. You build this, you predict this left-hand side through Bayes' rule. Yeah, that's very powerful. One last concept in probability models is this independence. Independence is if, for example, you try to compute, for example, probability of an event A given the information of event B. And the B is no longer informative, or A and B, they are independent completely. The occurrence of A does not depend upon the information that B supplied. In that case, the probability of A will stay as it is, whether you know the occurrence of B or not. For example, let's say A is event that you roll a die, let's say, and A is an event that an odd number appears, 1, 3, and maybe 5. That's an event A, that an odd number appears. So the probability of A is 1/2 if we assume the equally likely faces, all the faces are equally likely. The probability of A, so let me write that here, probability of A, that is 1/2. But what if I say that what is the probability of A given the information that is not useful, or about an event that has nothing to do with A? The probability of A will not change in that case. Although if we know that event must occur and stuff like so. In that case, we say A and B, both the events, they are independent. So if the information if A and B are independent, then knowing the occurrence of B does not affect the probabilities on A. And that means the events A and B, they are independent. And a direct consequence of independence is that probability of A and B can be written as probability of A and probability of B, rather than writing, because if we write it in this way, then if they are independent, then these two are equivalent. So that's what independence means. In several cases, when we read real kind of data, there are several features in the data, and some features are independent from the other features. And when we build probabilistic models on those kind of features in a joint way, we will see the joint distributions later on. It is basically possible to exploit that independence information to build more concise, more efficient, and more valuable probabilistic models as compared to otherwise. Conditional independence is another concept. Sometimes, for example, maybe it is possible that the event A and B, they are not independent, which means A intersection B is not equal to A and B, it is, let's say A and B, they are not independent, but it may be possible that given an information about some other event, maybe some other event has occurred. Now it may be possible that the two events, they become independent given this information about the third event. And in that case, we say A and B, although they are not independent, but they are independent conditionally, conditioned on this event. And this is possible. Maybe A and B, they depend heavily on each other, but once another event, the information about another event is available, given that information, A and B, they may not depend on each other heavily anymore. So yeah, so that's about the very basic theory of probabilistic models in terms of events and sets and all that kind of stuff. I moved very basically from set to these kind of models and probability laws and axioms and all that stuff. In the next video, we will be moving from events to variables called the random variables. And these are the random variables that are much more important, because when we read real data from different files to build probabilistic models on that, these real data, the attributes of that data, they actually are variables and called random variables that eventually represent certain events inside. But working with the variables, working with the numeric data in terms of variables will give us much more statistical analysis as compared to events. For example, we can compute the averages, we can compute the expected values, variances, spread of the data, and spread of a particular variable, random variable that represents an events, for example. So representing events in terms of variables, random variables, to come up with a numeric form will give us a very powerful tool to work with real data, the real data, and to analyze the real data. So in the next video, in the next video series, we will start from random variables. We will convert events to variables to numeric form. And there we will actually be playing with all the real kind of data using all the concepts that you have seen here in this particular video. We will extend these concepts to variables and then to real data, and we will actually build very beautiful models, probabilistic models and statistical models on real data. So if you like this content, please subscribe our channel and like this video and share to your friends and press the notification button so that whenever our new video or new notifications they come, you get notified immediately. So hope to see you in the next video series.